Surface Plasmon Resonance, or SPR, has emerged as a powerful optical detection technique for studying label-free biomolecular interactions in real time within a variety of diverse applications, such as life science, electrochemistry, chemical vapor detection, food and environmental safety, and beyond. Due to its simplicity, nearly every commercially available SPR instrument uses a detection scheme called the Plasmon configuration. In this setup, a light source passes through a prism, reflects off the backside of the sensor chip surface, and into a detector. At a certain incident angle known as the resonance angle, light is absorbed by the electrons in the metal film of the sensor chip, causing them to resonate. These resonating electrons are also known as surface plasmons, which are sensitive to the surrounding environment. The result is an intensity loss in the reflected beam, which appears as a dark band and can be seen as a dip in the SPR reflection intensity curve. The shape and location of the SPR dip can then be used to convey information about the sensor surface. SPR technology is commonly utilized for the study of molecular binding interactions between free analyte molecules in solution and probe molecules which are linked to or immobilized onto the sensor surface. As a molecular binding event takes place, the angular position of this dark band shifts, and a shift in the reflectivity curve can also be observed. This is a direct method of detection which avoids the drawbacks of labels. Another powerful aspect of SPR technology is in its ability to observe the time-dependent binding interaction between molecules. By monitoring this change in SPR response over time, researchers can study the kinetics of molecular binding events. In the first example, an analyte with low affinity to the immobilized ligand on the sensor surface is introduced, and therefore negligible binding interaction is observed. However, when an analyte with higher affinity to the immobilized ligand is introduced into the system, then binding events are more readily observed. Initially, there are many binding sites available, resulting in a rapid increase in SPR response that occurs as analyte begins to bind to the ligand. While sample is continually delivered to the sensor surface, analyte molecules continue to bind, and the number of available binding sites decreases, corresponding to a decrease in binding rate. As the SPR response levels off, the system approaches equilibrium, and the number of molecules binding and unbinding become equal. When no more analyte is introduced into the system, the molecules will continue to unbind, resulting in a decrease in SPR response. The association constant, Ka, can be extracted from the behavior of the binding response, and likewise, the dissociation constant, Kd, can be extracted from the unbinding response. The ratio of these two rate constants can yield the binding affinity of the system. The information that can be obtained from SPR serves as a simple, precise, and label-free technique for quantitative analysis of molecular binding interactions.